All right, welcome to the third review session or review video for the semester. We're reviewing for exam 3, which covers chapters 7 and Appendix B. All right, so we're going to start off by just going through the old exam 3 from last semester. And the first problem of which is to find the eigenvalues and eigenvectors for this matrix here. So anytime that you want to find the eigenvalues and eigenvectors, you start by finding the eigenvalues via finding the roots of the characteristic polynomial, determinant of a minus lambda I. So we subtract lambda times the identity matrix, which basically has the effect of just subtracting lambda along the diagonals. And then we just use our 2 by 2 determinant formula, 1 minus lambda times 8 minus lambda minus 10 times 3. And now we want to find the roots of this. So this is equal to lambda squared minus 8 lambda minus 1 lambda. So minus 9 lambda plus 8 minus 30. Or minus 22. So this then factors as lambda minus 11 times lambda plus 2, which tells us that our roots, our eigenvalues, are 11 and negative 2. So then we move on by, for each eigenvalue, we find the solutions to a minus lambda I times v equals the 0 vector, and sort of the shortcut way of writing this out, just because this is homogeneous, everything is equal to 0, we can just kind of row reduce a minus lambda I. So lambda is 11 here, and so a minus lambda I, so a is this. So minus 11i, we just subtract 11 along the diagonals. You can think of it as just plugging 11 into this matrix up here. So 1 minus 11 is negative 10. 8 minus 11 is negative 3. So maybe first thing I would do is scale down row 2 by dividing it by 3. And then I would do 10 times row 2, add it to row 1. Plenty of ways that you could go about doing that. Like you could scale down row 1 first and then 0 out row 2. It doesn't really matter. We end up getting that x minus y is equal to 0. So x is equal to y. And your eigenvector, you just have to choose any non-zero vector, x comma y, that satisfies that the x and y values are equal. So you could do 1 comma 1 or 2 2. Anything other than 0 0 would be fine. All right, a minus negative 2i, so a plus 2i, ends up being 310, 310. All right, add 2, there should be 3 and 10. All right, and then we'll just simply do negative row 1, add it to row 2. And this tells us that 3x plus 10y is equal to 0. So you do a bunch of choices here. Like if you don't want to have fractions, so you could just solve for x and then choose like y equals 1 and then figure out that what x would be equal to. It would end up being like a fraction or something like that. If you want to avoid fractions, the trick here would be to make x be whatever that coefficient of y is. So if you make x be 10 there, you get 3 times 10 plus 10 times, now y will end up being the negative of this coefficient, because then you'll get 3 times 10 plus 10 times negative 3, so 30 minus 30 does equal 0. So that's kind of the trick to avoid using fractions there. So those are your eigenvalues and eigenvectors. If you want to be more specific about the eigenpairs, -2 goes with the vector 10, -3, and then the eigenvalue 11 goes with the eigenvector 1, 1. Because the order, like this eigenvector is attached to that eigenvalue. Same with like this thing over here. All right, anyway, moving on. Computing some Laplace transforms. 3 times delta of t minus 5, convolution with e to the t. So if you're just doing the Laplace transform of one function, convolution with another function, you don't want to actually compute the convolution. You just, because the Laplace transform of this convolution just ends up splitting up as a product. So 3 times delta of t minus 5, do that Laplace transform, multiply it by Laplace transform of e to the t. Laplace transform of delta of t minus 5 is e to the -5s. Laplace transform of e to the t is 1 over s minus 1. All right, t times sinh of 2t minus t to the 4th. So Laplace transform of this. So because it's a sum, it splits up as a sum, or I guess difference, of these two Laplace transforms. Don't know what happened there. Okay, so t to the 4th, Laplace transform of that is 4 factorial over s to the 5th. That one's just directly from the table. And then Laplace transform of t sinh of 2t. Anytime that you have t times a function that you know the Laplace transform of, it's going to be negative the derivative of whatever the Laplace transform of that function is. Okay, so this is negative derivative of, and then we can look at the table and see that the Laplace transform of sinh of 2t, I believe, just going off memory, this is 2 over s squared minus 2 squared. By the way, 4 factorial is equal to 24. So I'll just write it like that. And if I want to take the derivative of 2s squared minus 4, I'm going to write that as s squared minus 4 to the -1. Remember that we're not taking any derivatives over here. That's just totally different, totally separate. So this becomes, all right, so we have the negative out there, but then we bring this negative down. So we get a double negatives, positive, 2 times s squared minus 4 to the -2. And then by the chain rule, times the derivative of the inside, s squared minus 4, derivative of s squared minus 4 is 2s. And this would be our answer. Of course, you could simplify this, 4s over s squared minus 4 squared. Okay, e to the t times cosine of 3t. Laplace transform of this. So whenever we multiply by e to the t or e to the kt, anything like that, this is going to be a translation of whatever the Laplace transform of cosine of 3t is. But instead of just like having it be, just having a regular old s in there, it's going to be an s minus 1. So we're going to replace all of our s's with s minus 1s. So remember that this notation means function composition. Just kind of looking at the formula that I'm using it here. You could think of this as, so f of s, capital F of s, is your Laplace transform of little f. And so you figure out what that Laplace transform is, and then you just plug in s minus a instead of s. So we're just using this. Okay, so then Laplace transform of cosine of 3t, that's s over s squared plus 9. But instead of s's, we want to use s minus 1. So I'm going to replace all of my s's with s minus 1s. So s minus 1 over s minus 1 squared plus 9. All right, inverse Laplace transform of the following functions. So we have e to the negative 5s. Let's look at the table for this one. So we have like an e to the constant times s, right? So e to the ks. So we're looking for something like that in the table. Not here, not here, not here, 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 or here. So it's not any of those. Okay. All right, well, are there any formulas over here that might help us do L inverse of e to the something? So these are like the Laplace of stuff. The right-hand side is like L inverse formulas. L inverse, so it's not a translation. Here we have L inverse of e to the negative as times a function. So maybe that's helpful. Let's look at that. So L inverse of e to the negative 5s. So we have times 1, right? So it's not really times anything, so it's technically times 1. So this is L inverse of whatever your f of s is, but then evaluated at t minus a, so it's like a composition. We do L inverse of 1, but then plug in t minus 5, and then times u sub 5 of t. Okay, so now we just need to know, well, what's L inverse of 1? So if we go back up here, we notice that L inverse of 1, it's not actually a thing. It's not in the table at all, so this is a problem. So we run into a problem right here. And if you remember, when we were doing 7.5, I mentioned that there isn't any function whose Laplace transform is equal to 1, or any nice function whose Laplace transform is equal to 1. But for whatever reason, the Dirac delta function kind of like fills in a void that kind of helps us like get around that a little bit. So the Dirac delta function is way down here at the bottom of this table, because we learned it last. So Laplace transform of the Dirac delta function is actually equal to e to the negative s times a constant. So this is actually exactly what we're looking for. So if this were like in the table up here, we probably would have just stopped up there. So this right here, we get stuck right here. This is a problem because we can't do L inverse of 1. This doesn't really exist in like a nice sort of way. But this tells us that L inverse of e to the negative 5s, my 5s look like s's, is equal to delta of t minus 5. Okay, so this is a really quick problem if you just kind of recognize that delta of t minus 5, Laplace transform of that is just e to the negative 5s. But if you don't recognize that, then you kind of have to do like a whole thing. So it's delta of t minus 5. Very little like work that kind of goes into it, but maybe a decent amount of thinking. Okay, B, we have 1 over s minus 2 squared plus 9. So when I see this like s minus 2 being squared instead of an s being squared, that tells me that it's probably a translation. So if I do L inverse of 1 over s minus 2 squared plus 9, this is a translation by 2 units, which tells me that there should be an e to the 2t in there. So e to the 2t times L inverse of 1 over s squared plus 9. What's the formula that I'm using here? I'm using this right here. So if I see something that looks like a translation, that tells me that it's kind of coming from this formula over here. So if you do L of e to the at times a function, you end up getting a translation which replaces all your s's with s minus a's. So if you see something that has s minus a's instead of s's, that tells you that you had to have started with e to the at times something. So we could just do e to the at times L inverse of whatever the function is without the translation. So for us, 1 over s minus 2 squared plus 9, translation is by 2 units, so there should have been an e to the 2t there. Then we do L inverse of 1 over s squared plus 9. L inverse of 1 over s squared plus 9. So in the table, this is almost sine of 3t, but sine of 3t would give you 3 over s squared plus 9. So we're missing that 3. So we need to divide by 3 to compensate. So 1/3 of sine of 3t. Okay, last one, we have e to the negative 2s times 4 over s to the 5th. Let's just copy the thing over here. So I'm just going to bring this up. All right, so we have e to the negative 2s times some function that we can do the inverse Laplace transform of. So this tells us to just do that inverse Laplace transform of that guy. But then at the end of that, replace all of your t's with t minus a's. This is like function composition notation over here, not multiplication. The multiplication is over here with the dot. Then at the end, we multiply by u sub a of t. So which is going to be u sub 2 of t for us. So here we're going to get that L inverse is equal to L inverse of, or let me say L inverse of e negative 2s times 4 over s to the 5th is L inverse of 4 over s to the 5th. But then at the end, we'll plug in a t minus 2. And then we'll just multiply by u sub 2 of t. You could, of course, write that as u of t minus 2 if you want. I don't really like that notation, but it's fine if you do. Okay, L of 4 over s to the 5th. So this is almost going to be like t to the 4th. So in the table, Laplace of t to the 4th is 4 factorial over s to the 5th. So we're missing that factorial. So 4 factorial is 4 times 3 times 2 times 1. So we're missing the factor of 6 over here. So this is 6. So we need to multiply and divide by 6. So this is 1/6 of L inverse of 4 factorial over s to the 5th. And that is equal to, okay, so that should give us t to the 4th. But again, because of this t minus 2 over here, we have to plug in t minus 2 every time we see a t. So this is really t minus 2 to the 4th. And then times u sub 2 t. So that's our Laplace, inverse Laplace transform. Okay, using the definition of the Laplace transform to show that this this thing in the formula in the table is true. So the Laplace transform of e to the t, by definition, you should know this definition because this is not on the giant formula sheet. This is the definition of the Laplace transform. I think is important enough that it's the one formula that you need to just know coming into this. So 0 to infinity, e to the negative st times whatever your function in here is. So it's e to the t for us. So we just need to integrate this. You're gonna get stuck if you do anything other than just like splitting this or writing this as just e to the negative st plus t right here, just kind of combining those into like one exponent. Like if you do like a u sub or integration by parts thing or something like that, it's just not going to go well. So this is e to the negative s plus 1 times t. Personally, I would probably not even write that step. I would probably just jump straight to right here, but figure it can't hurt to write out all my steps here for an instructional video. All right, so e to the negative s plus 1 t. Integral of that is going to be 1 over that constant there. And then 0 to infinity. Because we're doing an integral from 0 to infinity, we're going to really do limit b goes to infinity of this whole thing from 0 to b. So I'll plug in b for t. And then minus, wait, well, this negative over here was kind of in a weird spot. Yeah, looks better. Okay, minus 1 over negative s plus 1, e to the negative s plus 1 times 0, so just e to the 0. This over here, so negative s plus 1, we usually assume s to be like as large as we need it to be in order for this thing to converge. It's for this limit to go to 0. And so this does go to 0 if we assume s is bigger than 1. Because if s is bigger than 1, then negative s plus 1 is going to be a negative number. So e to the negative b, as b goes to infinity, that goes to 0. If this was a positive number, this limit would be infinity, but it's a, it's negative, so it goes to 0. All right, so all in all, we get 0 plus or minus 1 over negative s plus 1, and if we distribute that negative, we get positive s minus 1. And then e to the 0, of course, is 1. Just noticed that that was a weird typo. That doesn't affect the problem at all. Yeah, we're just going to solve this IVP here. Okay, so we do L of y double prime plus y is equal to L of 4 times u sub 5 of t. Okay, so yeah, this is our classic IVP problem solving with like Laplace transforms. So this is not something that you would have been able to do in like any of the earlier sections. Like you pretty much have to do Laplace transforms on this one if you're gonna stick the material that we learn in our class. So the way that you go about solving these IVPs using Laplace transforms is you take Laplace of both sides, solve for capital Y of s, where Y of s is equal to just the Laplace transform of little y of t, I guess. And then once you solve for capital Y, then you go back by doing an inverse Laplace to get back to little y of t. So Laplace transform of y double prime is s squared y of s minus y of 0 times s minus y prime of 0. And if you don't remember that, that's conveniently over here in the table, this little spot right here. Most of the time you're just going to be working with these two things over here. This third one, not really going to come up too much, but that's like the general pattern for stuff. Also remember that L of just y by itself is just equal to, is just equal to just regular old capital Y of s. Maybe I'd write that. L of y is equal to just y of s. That's just by definition. And then these are like more like a theorem or result. So that's L of y double prime. Now we add L of y. What's L of y? It's just capital Y of S. Okay. Then on the right side, we have the Laplace transform of 4 times u sub 5 of t. So we have to use this formula over here. Let's bring that up here. So we can. So L of 4 times u sub a of t is equal to e to the negative as times something. So e to the e to the negative as, no, so negative 4s times L of, and now we do, so we have whatever our f of t is, but every time we see in t, we replace it with t plus a, or t plus 4. So our function is just f of t equals 4. So what is f of t plus 4? So every time we see a t, we replace it with 4. There are no t's, so we don't have to replace anything. So just 4 just stays as 4. So this is e to the negative 4s times the Laplace transform of 4, which is just 4 over s. So that's the Laplace transform of 4 times u sub 5 of t. Of course, the common mistake that I saw on this problem last semester was people would say they would get e to the negative 4s times not L of 4, but they do like 4 plus 5. They're like adding 5 to their f of t, but that's different. That would be like f of t plus sorry. Sorry. I was explaining stuff wrong earlier, but like the conclusion was correct. Your f of t was equal to 4, so your f of t, it should have been f of t plus 5, not f of t plus 4, which is what I was saying. Doesn't affect any of the final results. Your f of t plus 5 is still going to be equal to 4 because f of t is just always equal to 4. So everyone, like a lot of people last semester made the mistake of, they were doing f of t plus 5. That would be 4 plus 5, but that's different from what we have over here. So this is really just going to be 4. Okay, anyway, let me get rid of all of that because there's a lot of incorrect math over there. Don't want it on the screen. All right, let's get rid of that. Great. So this is the correct thing. Left-hand side, y of 0, 0, y prime of 0 is also 0. So these things are just going to go away. So we get s squared y of s plus capital Y of s. We can factor out a capital Y of s, be left with s squared plus 1 times y of s. Then capital Y can solve for it by just dividing by s squared plus 1. Like so. Okay, we're now going to want to do L inverse of this right-hand side. I can already sort of tell that L inverse of this thing, we're going to need to do some partial fractions on that. So let's do that. So it's going to be a over s plus bs plus c over s squared plus 1. Remember, this is degree 2 thing, so we need a degree 1 thing on the top. So we get 4 is equal to a times s squared plus 1. I'll just distribute right away. Plus bs plus c all times s. So I'm just multiplying everything by this denominator over here on the left and right hand sides. All right. So what do we get? Those are our s squared terms. We got our constant terms, and then we got that term over there. So c is just straight up going to equal 0 because there's no s terms. A is going to equal 4, and then a plus b is equal to 0. So b has to equal a -4. B and A are opposites of each other. Okay, so y of t is equal to L inverse of e to the -4s times, now instead of 4 over s squared plus 1, I'm going to write that as a over s, so 4 over s, plus bs plus c. B is -4, so we get -4s plus c, which is 0. Don't have to write that. Probably normally wouldn't write that. Again, just instructional purposes. Yeah, so we get that. Okay, now we just want to do L inverse of all this. So L inverse of, what do we do when we have L inverse of e to the -as times something? So let's go to the table over here. We're going to use this boy. Let's put that over there because we can. Okay, so L inverse of e to the -as times some function. We just do L inverse of that function as normal, but then at the end replace all of our t's with t minus a's, and then we multiply by u sub a. So we do L inverse of 4 over s plus, or I guess minus 4s over s squared plus 1. Because this is a this is an e to the -4s thing, so a is 4, so we replace all of our t's with t minus 4's, and then multiply by u sub 4. Okay, L inverse of 4 over s is just 4. L inverse of 4s over s squared plus 1 is 4 times cosine of t. Okay, and so now at this point, then we have to replace all of our t's with t minus 4's. So 4 times cosine of t really becomes 4 cosine of t minus 4. And again, same concept as before. If I were to replace 4 with, replace like our t's with t minus 4's over here, like that doesn't make sense. Oh no. Wait. These are all supposed to be 5's. Great. Should be a 5 because it was the use of 5. Great. Okay. We're too far into the video to re-record everything, so I'm just gonna yeah, we're at the end of this one at least, so I'm just gonna fix all this. All these, this was like u sub 5's, so these should have been e to the -5s's. I guess 4's are too close to 5's in my head. So this should have been a t minus 5. This should be a t minus 5. This should have been a u sub 5. Okay, I think this is going to end up being correct, probably. Yeah, okay. Yeah, this is correct. Not a, yeah, okay. Thankfully, that did not destroy everything too much. Yeah, all the 5's just needed to be 4's. Or 4's needed to be 5's, rather. Okay, so catching my train of thought, though. This was, so L inverse of, like, 4 over s was 4, and then we're supposed to replace all of our t's with t minus 5's, but there aren't any t's to replace over there, so don't really have to do anything. In 4 times cosine of t, we do replace our t with t minus 5, and we do get this. But yeah. called another 5. That should also be a 5. Okay, so just reviewing. So L of y double prime plus y, did the formulas over there, plugged in. Those things should have just been 0. If they were like a 1 and a 2 or something like that, you'd have to like add them over first. And then we factored out a capital Y of s from everything, and then divided both sides by s squared plus 1. Our right-hand side, 4 times u5 of t, because this was u5, we had an e to the negative 5s times L of just 4. There was like, we're replacing our t's with t plus 5s over there, but you know, there weren't any t's, so we just get 4 over s for that Laplace transform. Once we get here, we do partial fractions just on this thing. We don't really have to worry about the e to the negative 4s when we're doing partial fractions on that. And then we do L inverse of all this stuff. We have to apply that formula over there, which just pops out a u sub 5 of t again. And then we'd have a 4 over s minus 4s over s squared plus 1. L inverse of that thing is 4 over is just 4. L inverse of that thing is 4 cosine of t. Replace the t's with t minus 5s, and then you got the u sub 5 over there. All right, so that's it for the old exam from last semester. Let's look at the practice exam as well to see if there's anything else that's kind of different enough to warrant including in the video here. So I think this one probably warrants that. So f of t is equal to 5t or is equal to 3t squared, depending on where t is between. So the trick here is to recognize this as f of t equals 5t plus u sub 4 of t times 3t squared minus 5t. So this is a trick that we discussed in, I forget what section of the notes it was. I think it was 7.3. But yeah, so we discussed that trick back then. And so to do Laplace transform of this, we first write f of t like this, and then we compute the transform. So L of f of t is going to be L of that whole right-hand side. So we'll do L of 5t plus L of u4 of t times 3t squared minus 5t. L of 5t is 5 over s squared. And then how do we do L of u4 of t? When we do L of u sub a times a function, we do, let's put this off to the side, L of f of t times u sub a is equal to e to the negative as times L of f of t plus a. Okay, so over here we're going to pop out an e to the negative 4s and then do L of, well, this is our f of t, so we replace all of our t's with t plus a's, or t plus 4s, because this is u sub 4. So 3 times t plus 4 squared minus 5 t plus 4. Okay, I'm going to get rid of that. All right, so now we just have to do this whole thing. So just a little bit of algebra to do here. So this is going to be 3 times t squared plus 8t plus 16 minus 5t minus 20. Wait. actually double check the formula just quick. Yeah, e to the negative as times f of t plus a. Yeah, so we should replace all our t's with t plus a's. Sorry, I'm just second guessing myself a little bit. Yeah, t plus 4s. Okay, okay, good. So we get 3t squared plus 24t. 24 minus 5 is 19t. Plus 48. 48 minus 20 is 28. Okay, so just kind of simplifying stuff. All right, and then doing those Laplace transforms. 3t squared transforms into 3 times 2 over s cubed, which you could just write as 6 over s cubed if you want, and then 19 over s squared, and then 28 over s. All right, so that's our Laplace transform. Okay, cool. Yeah, this one's kind of different. Okay, so maybe I'll skip the partial fractions one. So option 1 would be partial fractions. I'll skip that. Partial fractions. I'll skip that because we've already done some partial fractions things. Because this is like 1 over s squared times s squared plus 1. And then option 2 would be to do the convolution theorem. So this is 1 over s squared times 1 over s squared plus 1. And so when you have a product of two things, you could split that up as a convolution of the inverse Laplace transforms. So this is really the convolution of 1 over s squared star 1 over s squared plus 1. 1 over s squared, L inverse of that is equal to t. L inverse of 1 over s squared plus 1 is sine of t. So we need to compute the convolution of t and sine of t. I think it's probably going to be a little bit easier if we reverse the order of this, because remember, order doesn't matter when we're doing convolutions. These two things are equal. So convolution is equal to the integral from 0 to 2 of sine of tau times the other function. Replace all your t's with t minus taus. I just think it's easier to replace the t's with t minus taus for that function than it is to deal with like sine of t minus taus. That's just me though. And then integrate with respect to tau. All right, we're going to do integration by parts here. U is going to be t minus tau. dv is going to be sine of tau d tau. So v will be negative cosine tau. du will be negative 1 d tau. So this becomes uv, so negative t minus tau times cosine of tau from 0 to t. Yep. Okay, and then minus the integral of v du. V is just cosine of tau, negative cosine of tau, and then du is negative d tau, so we got a double negative inside of there, then d tau. And then integrate from 0 to t. All right, so this is negative t minus tau cosine of tau, and then minus the integral of cosine, which is sine of tau. And everything now is from 0 to t. So we get, plugging in t's, we get t minus t is 0. And then minus sine, sorry. Those should be t's. Getting too excited. Yeah, t minus t times cosine of t minus sine of t. That's what we get when we plug in t's. And now we subtract what we get. So everything's going to be like double negatives now when we plug in zeros for tau. So now t minus 0 is just t, cosine of 0, and then plus sine of 0, which is just going to be 0. That's 0, that's 0, That's just sine of t plus t. So we get negative sine of t plus t. Or just t minus sine of t. Yeah, and that's what you should also get that same answer just using partial fractions. So yeah, same thing for both. Okay, cool. Let's see. Was this IVP, was this one worth including in the video? I don't think so. It's pretty similar to what we did in the other one. Let's see. This one also kind of similar. It's just kind of good working through it on your own. I have like all these solutions are already posted on Husky CT, so please take a look at those. At this point, I'm just kind of doing anything that's like kind of different enough to be worth including in the video. All right, this one's a little different. So t squared plus 1 squared. So this one, I mean, it's not too bad. You just kind of have to like expand everything out. So this would be t to the 4th plus 2t squared plus 1. So then the Laplace transform of that would be 4 factorial over s to the 5th plus 2 times 2 factorial over s to the 3rd, and then plus 1 over s. Let's see. This one I think is worth doing. T cosine of t divided by 3. So Laplace transform of this is going to equal, so because we have this t right here, it's going to be negative the derivative of whatever the Laplace of cosine of t over 3 is equal to. So we get negative derivative of, now what's the Laplace transform of cosine of t over 3? So cosine of kt, so like our k value here is like a 1/3. So cosine of kt is going to be s over s squared plus k squared. K squared is 1/9. So negative derivative of that. So we have to do a quotient rule. So we'll keep that negative out there. Derivative of the top is 1. Keep the bottom. Minus the top times the derivative of the bottom, which is 2s. And then all over the denominator squared. And so that would be your answer, and you could of course simplify this if you want. So this would be like s squared minus 2s squared is negative s squared, and then like plus 1/9. But then if you want to distribute this negative everything, it changes the sign of those, so it becomes s squared minus 1/9. And then the denominator just stays like so. Like so, yeah. And let's just do d as well. So Laplace transform of this is going to be Laplace transform of whatever cosh of t over 3 is, but then replace all of your s's with s minus your minus whatever this a value is. So s minus negative 2 is s plus 2. So cosh of t over 3, L of that, it's just like cosine, except it's s over s squared minus k squared. So it's just like a negative kind of cosine. So we get s over s squared minus k squared. K is again a 1/3, so minus 1/9. But then we replace all of our s's with s plus 2's, so this becomes s plus 2 in the top. You don't really need the parentheses, I just kind of put them there to make it more obvious what's going on. And then s plus 2 squared instead of s squared. And that's it. Notice that there were like 2 s's over here, so we're replacing all of our s's with s plus 2's, not just like one of the s's, you know? Yeah, all right. Some of these ones are a little harder. So, okay, let's come back to those. We will do that one. let's see, we won't do that one. Let's do this one just to be like a little bit different. Let's just kind of get away from the Laplace transforms a little bit. So if we want to solve this thing using row reductions, we first put everything into an augmented matrix, like so. And then we just want to row reduce and solve. So let's divide row 1 by 2. Scale it down a little bit. Go like that. Boom. Okay. And now I want to zero out this 5 right here. So I'm going to do -5 times this first row, add it to the second row to get rid of that 5 there. So -5 row 1, add it to row 2. -2 times 5 is -10. Add that to -1, we get -11. -5 times -3 is +15. 15 plus 2 is 17. Let's divide row 2 by -11. All right, so we got some gross fractions in here a little bit, but that's fine. We can handle a couple fractions in our life. So we'll do -2 times row 2, add it to row 1. Just to zero out this 2 above the 1. And then this stays -17 over 11, and this will be -3 plus 2 times this thing. So 34 over 11. So that's going to be whatever that value is going to be our x value. 3, if I want to find a common denominator of 11, that's 33 over 11. So this becomes just 1 over 11. And then our y value is just -17 over 11. So those that's our answer. That's our x value, that's our y value. All right, let's come back over here. Laplace. All right, this first one, you just want to multiply everything out first. So 1 over s squared, and then plus, it'll be like 1 over s to the 4th on the outside, and then our cross term is going to be 1 over s times 1 over s squared times 2. So it'd be 2 over s cubed in the middle there. So then L inverse of that. So L inverse of 1 over s squared is just going to be t. L inverse of 2 over s cubed is just t squared. And then L inverse of 1 over s to the 4th is, it's going to be like a 1/6 of t cubed, because there's like, if you had 3 factorial over s to the 4th, 3 factorial over s to the 4th, like L inverse of that is t cubed, and 3 factorial is equal to 6. So I'm just I probably could have written them both as 6, but I didn't. So yeah, this is plus 1 over 6 t to the 3rd. This guy here, this is 1 over s squared plus 3 times s squared minus 3. So we're going to do partial fractions on this one. So we're going to write it as as plus b over s squared plus 3 plus cs plus d over s squared minus 3. I don't know if I'm just getting lucky in this problem by not splitting up the s squared minus 3 into like s plus square root of 3 times s minus square root of 3, because it is kind of equal to that. So you could kind of split this up even further like that, but I'm not, and I actually don't know if I'm like just getting lucky or not. I just kind of know that this ends up working here. But anyway, so we'll do the partial fractions on that one, and then you'll kind of see what happens. All right, so we get 1 is equal to, so we'll do as plus b times s squared minus 3, and then cs plus d times s squared plus 3. So multiplying as squared plus b times s squared, we get as cubed plus bs squared. I'm going to do this in black. I'm going to highlight things. And then times negative 3 for all that, minus 3b. And then plus cs plus d times s squared plus 3. So cs cubed plus ds squared plus 3cs plus 3d. All right, highlighting things. We have our cubic terms there and there, squared terms here and here, s terms, and constant terms, and then we just have the one constant term on the right. So we get a plus b is equal to 0. We get, looking at the s cubed terms, the blue terms, a plus c is equal to 0. Wait, is that right? Wait. Wait, where'd I get a plus b is equal to 0? Hold on, let me start over. Okay, let's just look at those ones first. So a plus c is equal to 0. B plus d is equal to 0. Okay, this is better. Negative 3a plus 3c is equal to 0. Yep. And then negative 3b plus 3d is equal to 1. Okay, cool. So this tells us b is equal to negative d. So if I replace b with negative d over here, this would tell us that positive 3d plus another 3d is equal to 1. So 6d is equal to 1, so d is 1 over 6. And then b is just the negative of that, so it's negative 1 over 6. This tells us that a is equal to negative c. This tells us that a is equal to positive c. So c is equal to negative a, so that tells us that a is equal to 0, and so is c. So a and c are both equal to 0. If any number is equal to the negative of itself, if you had 5 is equal to negative 5, that doesn't make sense. The only way that can work is for that number to equal 0. So it's 0. So this thing, L inverse of that, is equal to, okay, so as plus b. So b is negative 1 over 6 for s squared plus 3. And then plus, sorry, I should say L inverse of that. And then plus L inverse of cs plus d. D is 1 over 6. Okay, cool. So we get negative 1 over 6 times L inverse of 1 over s squared plus 3. That's almost like a sine thing. Sine of kt is like k over s squared plus k squared. So what's our k over here? So s squared plus k squared. So k is going to be like the square root of whatever that number is, which is 3. So it's going to be square root of 3. So this is like L inverse of like 1 over s squared plus square root of 3 squared. And then it's going to be like a similar sort of thing over here. So we're missing like the square root of 3 here and here. So we'll like multiply and divide by square root of 3 for both of those. Like so. So now this is going to be sine of square root of 3t. And then this is going to be hyperbolic sine of square root of 3t. sinh of 3t. It's root 3t. All right, if we look at this, sine is s squared k over s squared plus k squared, and sinh is k over s squared minus k squared. Got it. Got it. Okay. Yeah. My guess is that you probably could have also written this as like using like the s plus square root 3, s minus square root 3 thing, and it probably would have still worked out great. I don't really know. I expect that it would work out. I'm pretty confident that it would work out. But I don't really. This works. I know this works. So I don't really want to work through that. I'm pretty sure it would work out if you wanted to. If you did that, I think you would just have some like probably have some like e to the kt things going on in there. So yeah, there's probably multiple ways of doing this problem. That's what I'm saying. Let's see. This one's worth doing. This one, we've kind of done a lot of things similar to it, so we won't. This one we'll do though. Okay, so 4 over... Okay, so we can't really factor this one. So what you want to do is do like a difference of perfect, or sorry, completing the square over here. So if this was like s squared minus 4s plus 4, that would factor as s minus 2 squared, right? It's not plus 4, it's plus 20. So we're going to borrow 4 from the 20, be left with 16. So now this is 4 over s minus 2 squared plus 16. And so this is easier to work with because now this looks like a translation. So L inverse of that is equal to e to the 2t times L inverse of 4 over s squared plus 16. And that is just sine of 4t. All right, cool. So that's that. Hopefully there weren't any major typos or issues other than the I was writing 4s instead of 5s for like the last problem on the other exam. But yeah, let me know if you have any questions. And yeah, good luck studying.